here, and that will tell us the compressive strength we need to match that. Okay? And you can check that out against different types of masonry. But would we have to do anything else if we're checking that wall? Okay, we have looked at eccentricities in this direction too. And if we have the wall, I need something that I can bend or buckle. No, well, paper's going to be a bit thin. You're a ruler. That's gone before we started. We'll have to do it with a few sheets of paper. Okay, we'll do it with a few sheets of paper. So we've got the wall like that. The load's coming on here. Right, I can probably do it like that. Okay. So we're looking at that sort of thing happening. Okay. And because that depth is big, you're not really going to have any problem with buckling like that. Of course, where you can get is that. So when we consider a wall like this, you do need to think of the possibility of that sort of thing happening. So how do we protect against that? That's where you have to, if we look at this wall here now, in section now. So we've still got our height H there. We've still got our load P coming down there, but the S is coming out that way, or coming in that way. So what we've made sure is, up at the top, the stress is right. But in a wall, you normally check it in two places. At the top and at the middle fifth. For that sort of situation. So if we do this up here, we've sorted out what happens under the slab. But you should really check that one there. If you do that, there are those formulae that we give you for eccentricity mid-height and how that's affected by slenderness. As far as this wall's concerned, that load is coming down the middle. So there's no eccentricity due to out-of-plane loading. The only eccentricity will arise out of the slenderness ratio effect. So the EMK, the EM, the bit at the top, will be 0. But there are some formulae. I just got a slide to show the. Yeah. This one would do it. It's a different problem, but it's a different problem. I don't know whether you can see it there, but that's EK, phi M, and U. There, how you deal with out-of-plane effects in walls. We wouldn't expect you to know those formulae. We'd give you those if you need them. But you would need to use these now to check this wall at mid-height. Here we've got eccentricities in there, capacity reduction factor, and there we've got a modifier U which sits in there. We'll give you those, so as long as you're familiar with them, the detail probably doesn't matter so much. But the effect that will come into play here will be the one due to slenderness. The bit due to slenderness is where the U comes in there. So we have no initial eccentricity at the top, so no eccentricity down the wall due to the applied load, only an eccentricity due to slenderness. So the EMK that sits in there will be 0. It's only the U effect you would need to consider. But you should check it in two places. At the top, using that, and in the middle for out of plane effects. That's in plane, that's out of plane. So if we just write that big, and that's in. And there's really not much more that we could ask you about this type of thing.
So you must be confused. You know, on that formula there, the central one, the E which doesn't have a subscript, which eccentricity is that?
No, that's exponential.
Oh, it's
E.
All right.
That's the exponential.
Do you have the answers to that to hand?
To what?
Do you have the answers of that question to hand, or not?
I might have. Have you had a go at it?
Yeah.
If you want to tell me afterwards, we can compare. But I might just come to that question in a minute and say a little bit about it. Is that okay for shear? Just one other thing on shear, and then I will come back to that. Okay.
All I got is a picture of it.
This is just another type of problem that you might get on shear. I can't remember, this was 2010. But here we had
How about if you had a lot easier?
series of walls.
Is it that? No. That's not it. That. Yes. Oh yeah, that's
Slab
obvious.
across the top.
No, actually, it's not obvious. Oh, this is just your exponential, yeah.
Okay. And we apply a load of on the other side. Doesn't really matter. We've got a distributed load on there.
Might as well follow it.
The walls. Plan.
Did you come with yesterday? Oh, is it?
They're all the same.
Oh, sorry, I got it. This I've got. That's what I understand. I don't understand this last year.
1200, 1800,
This last bit here.
1200 in there.
Might as well just follow it first.
I think those bits were 900. Okay, so probably said just determine the minimum design compressive strength of these walls. So actually the way you do it is in symbols, what I've just done before. We had a load of 70 kilonewtons per metre on there. So the first thing you've got to do is for each of the walls decide how much of that 25 kilonewtons goes into them. Now before we looked at three walls side by side and we shared the load in proportion to their stiffness. We do exactly the same here. So do we have letters on these? Now we'll call that A, B and A. So how would we find out how much load, given the height, 3.8.
So first.
So the load in A that's just going to come from looking at its stiffness relative to the stiffness of the whole. Sorry, 3.6. Yeah, I wasn't actually going to work through all the numbers, but thanks anyway. Okay, so how do we get the wall in A? The stiffness of the wall in A? Well, it's just that same thing. Sorry, how do we get the amount of load? Relates to its stiffness. So we just need the stiffness of A divided by the sum of the stiffnesses of them all. So that would be 2 times stiffness A plus stiffness B. Times stiffness A plus stiffness B. Okay. So we need for that EI over L for A, all times the load, which is 25 kilonewtons. So EI over L for A over 2 EI over L for A plus EI over L for B, all times 25. So, what's L in this particular case? This often seems to be a place where people get sort of mixed up. They're used to saying EI over L's and that sort of thing, and then they come to look at a problem like this, they get a bit mixed up by what's L. Is L that? Or is that L for wall A?
It's 1200 plus half of that.
Is it 3,600?
No,
Is it?
Over.
Pretty sure it's 3,600. No, you take
What's
thing
L?
and then
What's,
hang over.
what's providing the stiffness?
No, it's not.
L in this case
It's 3,600, yeah.
is the height. Because we're looking at the stiffness to resist that sort of bending. So quite a lot of people probably in doing this problem would have stuck L in as that. But if you think about it, we've got this cross section here resisting the bending. So it's like that doing that. So the L's the same for them all. So we can actually
I thought they might.
cancel that out. Now I think they're all made of the same material in this case as well. So if that's the case, we can get rid of the E's. If they weren't made of the same material, then we'd have to leave the E in. Sometimes you might find we give you a problem, say the E value for that is twice the E value for that. So in that case we could put, say, 2E here and E there, and you can see the E's would still cancel out. You don't need the actual numerical values. So that comes down to I for A divided by 2IA plus IB all times 25. Now what's I for wall A? It's a BD cubed upon 12. So for wall A, what is B? And what's D? We've got a 1200 and 150. Which way round will they go?
150 and 1,200 cubed.
Yeah.
150 be D.
B.
150 B.
D is 150.
Yeah.
Okay. So if we did that, we'd be looking at bending about that axis. So we want to look at it really about that one. B is 150. The D is, in this case, 1200.
Will you right or wrong?
Similarly for wall B. Again, probably that's somewhere people would have made mistakes in trying to solve this problem. All the B's are the same, so I don't think it's hardly worth it, but they'll have a BD cubed upon 12 for A, and B in there. You can cross all the B's out, you can cross all the 12's out. It's all just going to relate to this dimension. And then you do the same for wall B. Wall A we've got over there anyway. So once you've done that calculation, and it's really not very difficult if you see, I've spun it out a little bit there, but it's, what, 1200 squared over 2 times 1200 squared plus 1800 squared, all times are 25.
Cube.
So,
Cube.
Cube, thank you, yes. So it's really just a 1 or 2 line calculation. What you'll find is obviously that is going to take more load because it's stiffer, because once you put an 1800 cubed in there, of course you're going to get something much bigger than that. But that would then give you the force in the wall. And it's obvious if you do the sums that it's going to be wall B, the middle one, that's critical. Just by way of showing, what did we get? What did I get? Yeah, I got for that one the load in wall B. .7 kilonewtons in that, and wall A was 4.65, I think, kilonewtons. You may just have to round those up to get the 25. So now, this is by far and away the worst case. So all we're going to do is take that wall out. Got a load coming on there of whatever it was, 15.7 kilonewtons. A vertical load there, that was somewhere where probably people may... What would the vertical load be on wall B? 70 times something.
70 times 2.7?
Yeah.
Yeah.
Because it carries a load from there to there. So it'll be 70 times 2.750. So that would be the value of P. 2750 times 70. And there we are. So you know the vertical load, you know the horizontal load. You can work out the eccentricity E.
Eccentricity that boy.
And you can work out the
Eccentricity that boy.
FK.
Yeah.
As I just did a minute.
Should be that bit.
In the problem, it gives you these three formulae there, and it's then just a question of checking the middle fifth of the wall.
Yeah, but that scares me. That'll just mess me up.
So it's actually a problem, I think. It brings in quite a bit of what we've covered. It's got shear in it. You've got to think of the in-plane effects. This sort of thing here, you'll find another exam question says, determine the capacity reduction factor for a wall. Effectively, what we're doing here is what you do to calculate the capacity reduction factor. We're not calling it that, we're just working out the load that can be carried or the stress that's needed to balance that applied load. So it covers that. How you distribute shear, in-plane effects, how stress distributes in the wall, and the out-of-plane effect. In other words, it just brings in the use of these formulae for a check in height there. So it covers virtually everything in one question, or aspect of everything that is done. Anybody got any of the, or can you think of anything else about shear that might be an issue? No? Yeah?
When are we supposed to use the capacity reduction factor?
we did when we're doing middle bit.
Well, that's a capacity reduction factor. It can also come into play if I just get rid of all that. So, if we have a wall like that of thickness T, and it's carrying a vertical load P, and the moment M, then that's the equivalent of P being shifted somewhere over there, and you're getting a stress distribution that looks like that. This is now the thickness of the wall. So I've got to draw it wide, otherwise one can't see what's happening. But this is thickness, whereas before we were looking at length. The capacity reduction factor is the value of that load divided by what would happen if that load remained concentric. Capacity reduction factor is the ratio between that and that. Just looking at that problem there that I've got there. We did actually, I think I did go through this at the end of last term. Let me just remind you, because it shows, I suppose, another facet of what we're doing. It starts off by asking what are the differences between the way BS5628 and EC6 calculate eccentricities. BS5628 assumes a triangular distribution of stress under the bearing onto a wall, and the axial load concentric at the bottom of the story height. It's all in the notes. You can sort of, I'm really just replicating that. EC6 says we use a frame approach. So they're the two different, or a sub-frame approach. So the first bit of this, we've got a structure like that, and it asks you to calculate the eccentricity of the central wall just below the first slab level. Well, the sort of thing using the EC6 approach, as I think I said during the lectures, look back over the last 4 or 5 years, EC6 has been coming into use much more in this country. Before that, even though it's sort of hanging around there in the background as a draft, people were using BS5628. And in practice even today, because many people would say BS5628 is easier to use, it is still used quite a lot. The only reason one can get away with using it is because the building regulations in this country recognise the British standards. So until the building regulations get changed, there's a let-out to use British standards. So people still do. But anyway, what we've tried to do in teaching the course, we've tried to move on and bring people along. So if you go back 4, 5, 6, 7 years, you might find questions that actually asked you to numerically calculate an eccentricity using one approach and then the other. But in this one it says do it all using EC6 in there. So it's just a subframe. So all we do is that, and we call that floor. Wall. Okay. They're the same in terms of geometry, so you don't have different names. So to get the eccentricity, what we do is we calculate, assuming subframe like that, we calculate the moment that occurs at the joint in this wall here. So we're going to try and calculate the bending moment there. And if we know the bending moment and we know the vertical load coming down, as far as our cross-section is concerned, we'll have an M and a P. So what we want to do is calculate the M, because once we've got the M, we can determine the eccentricity. the eccentricity is given by, perhaps easier to remember it, P times E is equal to M. So eccentricity is M over P. I think sometimes in the heat of exams and elsewhere as well, one can get those mixed up. So it's much better to think where it comes from. That way, less on. Okay, so what we need to do is calculate the out of balance moment here and share it into those four walls. We do that just using the distribution factor we've used in moment distribution. Now it's a long-looking formula if you look at it in the notes, but in fact all it is a distribution factor. So let's call that B, shall we? A, just to differentiate them. C and D. So the moment at the top of wall A is the stiffness of wall A divided by the sum of the stiffnesses there. So it's stiffness for wall A divided by 2 times stiffness for A, because we've got 2 of them. Oh, no, I've called them different numbers, so we'd have to say stiffness A plus stiffness B plus stiffness C plus stiffness D all times, say, I've used M over there, so we'll have, let's call it floor moment. Okay. The stiffness of wall A is just EI over L for wall A divided by EI over L for A plus EI over L for B plus all times floor and in the question it gives you, I think it says it gives you the relative values of the elasticity of the floor slab is twice that of the walls. So E for that is twice E for that. Not quite practical, but it just makes the arithmetic easy for you. So the E values will cancel out. We'll have L's in there. Were they the same? No, the L's different. You've got a 3,000 in there, 2,850. I've just tried to make them practical dimensions. So the L's will stay in. So now we need the I. And again, I is BD cubed over 12. Slab's 150 thick. Walls were 150 thick as well, I think.
How did anybody do that?
What have we got the thickness of the walls?
It says on the figure.
Pardon?
It says on the figure.
It does.
150.
150, yeah, 150. Okay, I thought so. So both the wall and the slab are 150. So what's B and what's D? And this is often the place where things go wrong. So what would be B and what would be D? We're looking at bending in that plane there.
Which plane? Bending that way and everything that way. Okay.
Yeah, but what value would you put in for B?
For all of them, it's the horizontal one.